Chapter 5, Section 3 is medians and altitudes of triangles. Okay, so first thing we're going to talk about is the median of a triangle. Okay, and the median of a triangle is a segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. So I have triangle ACG here. If I draw a line from A to CG and it splits the line into two congruent parts, so it hits at the midpoint, and then from G to the opposite side AC, and it also splits and hits at the midpoint, and then from C to E here, if E is the midpoint of AG, so two congruent segments here as well. Then you can say that AF is a median, CE is a median, and GB is a median of triangle ACG. Okay, so if you have two congruent sides here, two congruent sides here, and two congruent sides here, then all three of those are median. All right, now all the medians, if you notice, meet at one point. This is called the centroid. Okay, it's the point of concurrency of the medians of the triangle. So when you have three medians, they all meet at one point. It's called the centroid. Okay. Now, the centroid theorem states the centroid of a triangle, so this point right here, is located 2/3 of the way from the distance of each vertex to the midpoint. So from A to D is 2/3 of the way from A to F. Now, if you look here, I have the distance of AF, it's 9.18, and I multiply it by 2/3, I get 6.12. Well, here I also took the distance of A to D and got 6.12. It works the same way with each. 2/3 times GB gives me 4.99. DG is 4.99. 2/3 of EC, that's 4.61, and DC is the length from, or 2/3 the length of C to E, 4.61. So it still works, and I can move this triangle around. Okay, I move it, and notice the links still stay the same, even when I move it all the way around. Now, like the incenter, the centroid will always be inside the triangle. If I have an obtuse, if I have a right, it's always inside the triangle. Okay, and notice the numbers still are the same. Okay. All right. Now, the altitude of a triangle. Okay. The altitude of a triangle is basically its height. Okay, it's a perpendicular line from a vertex to the line containing the opposite side. So if you look here, right, it's pretty much almost like an equilateral triangle, so I'm going to make it a little different. Okay, so right here, E, if I draw the line from E to AG and it hits at point C, in order for EC to be an altitude, this has to be a 90-degree angle. Okay, from G to B, in order for it to be an altitude, it has to be at a 90-degree angle. From A to F, this has to be a 90-degree angle. Okay. Now, notice they all meet at the same point. All the altitudes meet at one point, right? And the point of concurrency for the altitudes of a triangle is called the orthocenter. Okay, the orthocenter. Now, this one is like our circumcenter. It can be inside the triangle. It can also be on the triangle for a right. So that's a right angle. Okay. And then for an obtuse, it can be outside. Now, you're wondering how can you draw a height of a triangle outside of it? Well, if you look, remember, the altitude of a triangle says a line containing the opposite. So it doesn't have to be inside. So look, E here, if I draw a line from E towards this actual segment here of GA, it's never going to form a right angle. But if I extend GA out like so, then it forms a right angle here. A to F, that's a right angle there. And G here, you extend AE, forms a right angle. Okay? So the orthocenter is a point where all the altitudes meet, the height of the triangle. Okay? And the height of the triangle must form 90-degree angles. Okay, so from E to GA here, extended, 90 degrees. From A to F, 90 degrees. From G to AE, extended, 90 degrees. And the orthocenter is outside. Okay, so for obtuse, it'll be outside. For a right, it'll land right on the vertex right there. And for an acute, it'll be inside. So like that.